This is our Project 3 presentation by Team 21. We'll be talking about our brainstorming decision-making process, as well as how our final project did in the final demo. Some introduction. A lot of nations are trying to develop technologies to do long-stay missions at Mars, including NASA. And long-stay missions would span about nearly 2 years, and this will require several resupply loads to be sent to Mars, as astronauts can be bringing them all at once when they land at Mars. And so this brings some challenges, which go into the objectives that are presented in the next slide. One of the main objectives for a Mars cargo rover or a macro is that it has to go through the terrain of Mars, which could include several obstacles, and the path might not be straight, so it has to deal with turns and stuff. And also the cargo must be delivered to a precise location, so where the astronauts will be staying during that mission, but also in the right orientation. Hence, the technology might be fragile or can only work one certain way. And next, we'll be talking about our brainstorming process when tasked with this project.
Okay, so the team's brainstorming process for this project, we wanted to make it extensive because it was the team's first major project. So we kind of broke it up into 3 different types of brainstorming techniques. Our first technique was the worst case scenario method. And in this method, we kind of listed different aspects of the macro that we wanted to find, the worst possible design for them. So we wanted to find the worst possible design for the frame, the wheels, motor placement, mounted motors. So each teammate had his own piece of paper and made the worst possible design. For the traditional brainstorming, we had a table talk. This table talk was about half an hour to 45 minutes, where each team member had his own time to speak about designs he wanted to see in the macro, or that would optimize the design. And in the last technique, we utilized the paper paths method. And in this method, there was one piece of paper that each team member wrote down his idea for, say, the wheels, and passed it to the next person. They wrote their idea for the frame type, and then passed it to the next person for another aspect of the design. This went on and on until there was a final design. And this process went through 3 times. And by the end of this process, we had 3-4 different designs that could be used. And then we wrote all these ideas down on a whiteboard and made sure we all understood what each person's hopes for design were and best ideas were. So that was our brainstorming technique. Next slide. Project management. This project, because again, it's our most extensive project to date, we wanted to make sure our timeline was very good. We were able to balance our customer needs versus our own needs. So we made a list of customer needs, which included being able to detect the magnet beacon, being able to detect the dashed line. The robot must be fast enough, so speed maintenance. The robot must be able to accurately place cargo on target, and the robot must be able to complete several rounds of deliveries. And these customer needs were all gotten from the Project 3 resources on Brightspace. And we had another needs finding table as well. And this one included a list of 4 more customer needs. This table is not pictured in the slide, but the customer needs included the ability to hold the payload, the ability to deliver the payload, the ability for the robot to operate autonomously, and the ability for the robot to safely navigate the Martian surface. And each of these charts, technical needs, technical requirements, and target values were created. And those different aspects were more so based on our ideas opposed to what the customer needed. But again, those ideas were meant to optimize the customer needs. That's it. Next slide. Okay, and go ahead.
Another part of project management is creating an effective timeline, so we can get our final product out by the deadline, which was in late November. So we started this project as far as designing and brainstorming in early October, and then we went into creating our preliminary design and testing that to get some data results, so we can make modifications if we need it, but also to get something done before the presentation of competence. And then based on that and further testing and further research about what we could do, we created more modifications to get to the final demo so it can do all the tasks that were stated in the objectives as well as the customer needs in the last slide. And throughout the process, we worked on a final report to record what changes we made in our design making process throughout the entire thing. You can go on the next slide.
Okay, so some of the ideas we wanted to implement into our robot was the tank treads for wheels. We also wanted to use fixed back wheels. We also attempted to use a claw to drop off the cargo, some line finders outside of robot, and we wanted to use a pie case.
And for the ideas that were presented in the last slide, they didn't come in our final macro design because they failed some portion of the test and the presentation of competence. For example, when we use our tank treads, they wouldn't be able to go up, since they're 3D printed, they wouldn't go up the ramp because it didn't have enough friction to go up the ramp. So due to that, we couldn't bring that in our final design. When we had the cargo hold behind the pie case and lower to the ground, it would tilt the entire macro backwards. So due to that being not a stable solution, we decided not to go with that process. And having a fixed wheel made it harder to turn, and it made it slower for the macro to turn overall and increase the turning radius. And due to several tests that we conducted outside and during the presentation of competence, we went away from these ideas as they didn't seem to be an effective solution for the objectives or for the final demo.
This is a front view and a back view of a robot. Next slide. Okay, so why use a conveyor belt to drop off the load? We tried different methods to drop off the load, but we figured out that using a conveyor belt was the most efficient method to drop off the load because, I mean, it's much easier, it requires less parts used, and it was very effective in dropping the load upright. Next slide. Why place line finders together? At first, we tried placing the line finders at the side of the robot, but we found out that it was very hard for the robot to stay in a straight line because when it's on the line and it goes up the line, it will have to, the line finder at the other side will have to detect the line, so it's going to turn, and it kept moving in a zigzag manner. So we figured out that the best way was to put it together, and that way it's easier for it to stay on the line. Why we didn't use treads as wheels? This was one of the ideas we wanted to implement, and we thought it was really cool to use tank treads as the wheels. However, this didn't pass the hill climbing test. During the hill climbing test, the tank treads couldn't grip with the paper hill, and it was very hard for the robot to climb the hill. So we have to scrap this off.
So some more information about the 3D printed parts that we had. At first, we tried to use some tank treads, but that didn't work out so well. But those were printed on a 3D printer, and that was about 40 hours of printing just for the 2 tank treads pictured here in the slide. Another piece that we did use on our robot was a custom designed pie case. We just took measurements off of the original pie case and added a little compartment on top for the supplied battery that we were given. And this was all done in a CAD software and printed on our own 3D printer. And that was the heart of our robot. The main code implemented a few smaller loops. We thought it would be easier, instead of repeating big blocks of code over and over, to use smaller user-defined functions. So we had a guidance loop where it was basically a line following mode. It would first ask if the magnet was detected through the Hall sensors. And if that was not true, then it would see if a line was detected on the left or the right side with the line finders. If it was detected on the left side, then it would try to turn left until it was not detected. And then if it was detected on the right side, then it would try to turn right until the line was no longer detected. And then when the line was not detected at all, it would just go in a straight line. So it just run through that loop over and over until a magnet was detected, then it would kick out of the guidance loop. Another loop that we defined was our unloading loop. And once it reached the final magnet on the course, it would run this. And so it would run the guidance loop for 3 seconds. This was to put the robot in a position where it could accurately dispense of the payload. Then it would stop and then run the loader motor, which was our conveyor belt, for 3 seconds. And that was to clear the cargo of the robot. Then it would return back into the guidance loop, which would bring it back onto the track and hopefully back all the way around in a big loop. Okay, so this is our larger actual flowchart of the code that we use. And so it all started and it would ask what test was being performed because we wanted to be able to tell the robot to go to the alpha, beta, or gamma landing site or to just run the speed test. So if we told the robot to run the guidance loop for the alpha landing site, then it would just run the guidance loop, turn right for 2 seconds at the first magnet, and then it would run the unload loop once it got to the other magnet. Once it finished that, it would go back into the guidance loop, and then it would just come back all the way around the loop. If we told it to go to the beta landing site, it would start off in the guidance loop, ignore the first magnet, and then do the same exact thing that it did on the alpha loop. And then for the final one, it would ignore the first and second, and then it would turn right, go back into line following mode, unload, and then go back into guidance. So those were the 3 main pieces where it could go to the 3 different landing sites. Our final and fourth input in piece of code was the speed test, and that was for the speed portion of the demo. And if this piece of the code was running, we could input the target speed and the time at which the motors would run. And we had a prepared spreadsheet with a bunch of values where when given the speed that we were trying to achieve, we could just look through that table and figure out a desirable combination of numbers to put in for these inputs. Some positive attributes of our robot was that we had a pivoting back wheel. So we had an all-wheel drive system with 2 wheels in the front and 1 wheel in the back. And the back wheel actually pivoted so we could turn a lot easier. And this made it really easy to get around sharp turns, not the sharpest turns, but it was a lot better than the original design. And the all-wheel drive really helped us get over obstacles easily. We had 2 Hall sensors instead of 1, so we could cover twice the area in case we were missing the magnet. So that worked out really well.
Okay, these are the negative attributes of our prototype system. Because we put an emphasis on systems thinking, our end result prototype system worked very well as a unit, but unfortunately we had certain individual aspects that did not function as we wanted. And that included the ultrasonic sensor, which did not detect the first sensor, and the Hall sensor reading that was overpowered by the line finder. And as we worked on this project, we realized that once we solved one problem, there was always another problem that came from that. So for example, at first we had the line finders pretty far out from each other, about 5 inches apart on the front of the robot. But then again, the robot would go on the black line and would start to diverge and go left and right. So we decided to put the line finders closer, and the line would follow the macro would follow the line for the whole entirety of the line. But then on turns and curves, it would start to diverge, and especially on dotted lines, it would start to diverge. So that's an example of how when we solve one thing, there's another problem. So definitely our robot was successful on individual tasks, but completing the whole unit of the track was pretty difficult. Next slide, please. So in conclusion, I feel like we were very satisfied with our macro. Again, I feel as though we feel as a team individually, we could complete the separate tasks of the track. We got over the hill successfully, got over the obstacles successfully, we got through the magnets. Unfortunately, we're not able to drop off the load because there was a malfunction with the code in the conveyor belt. So that was a little bit of disappointment. So overall, we could do three things differently. We could create a more reliable way of turning on the branch path. We could establish a way to better go through the tighter turn radius. So maybe we would, for that, put the line finders a little farther out. And we could improve curve dotted line following, which we were not able to get through on presentation day as well. So this has been Team 21's project. Thank you for listening. And if you have any more questions, please refer to our design notebook or our written report, which has even more details on our thought processes and how we got to our end macro. Thank you for listening.